So, how is everybody? Are we recording?
Yes.
Okay. So, lots to do, not a lot of time to do it in, so let's get cracking, shall we? I fell in a hole yesterday. I stepped on a manhole cover that wasn't secured, and I fell in. Yeah, actually it was this way. It was like, I could have broken my leg. It was terrible. I should sue. I am certainly going to be sending a tersely worded email.
Was it on campus?
Yeah, on the way to MLOT.
Was it around APB?
No, so you know, you go over the bridge.
Yeah.
Yeah? You know there's that little hill where, you know, the thing goes by? There are a couple of manhole covers there, not secured. Apparently, as I found out. Because, like, the thing is, right, I sometimes take that wooded path down on the other side of campus because A, it's a nicer walk, and B, it's like a slightly better route in terms of Euclidean distance, you know, slightly faster. There's no sidewalk going up from that, up that hill, around that bend, down to MLOT. So I was just cutting across the grass. I step on the manhole cover and, like, you know, down I go. Like, I could have easily broken my leg. You take a look at it. Like, see? Right? If I'd have nailed myself right here, I could have like, I don't know, popped my kneecap off or something. Anyway, I just wanted to let you guys know about this hazard, and for no other reason. So let's get into it then. So, we were talking about arrays. One thing that you are probably going to hate about C by the end of this is there's no default way of just printing an array like there is in Python. You know, in Python you just print array and it prints, or you print list and it just prints the list. In C, because everything is difficult in C, you actually have to write the code to iterate the list and then print each item in the list in sequence. So this code is a gift. I want you to take this code, write it down, put it in your notebook, and anytime you want to display an array, use this code. Okay? You will notice the use of our classic for loop. But yeah, relatively straightforward. Question?
Why is when you define the array, it's like C of 6 plus 6? Why is that?
That is merely to demonstrate that you can put any expression that results in an integer or natural number really in there, and it'll work.
Can you even typecast?
Yeah.
Cool.
Yeah. Typecasting is something we're going to need to talk about. That's like not as in the slides as maybe it should be. So, I learned recently that the C course that I teach the computer science students, it turns out that the course that requires that course is pretty heavy into typecasting. So I might try out some typecasting material on you guys this semester. But anyway, so know it, learn it, love it. In terms of visualization, if you needed this visualization, if you have an array C, each one maps to a particular memory cell, each containing a value. This should be relatively straightforward. Any questions? So, here are a few errors that might be considered. So first of all, let's take a look in the original guy here. You'll notice this line here where we are printing the array as an integer. Now this array is an integer array, but it will be noted that this does not result in the operation that you want. We're also using this mysterious P. Does anybody have any idea what the P stands for? If you've been paying attention in class so far, you know it's pointers. Very good. So this program produces the following warning. Format D expects argument of type integer, but argument two has type integer star. Do we know what the star means?
Pointer.
It means pointer. So int star means that this is an integer pointer. The array name itself, with no indexing operation attached to it, is a pointer to the first element of the array. Important knowledge. So you can see, if we view the output of this program, interpreted as an integer, we get this big long negative number. This is the second such time we've discussed big long negative numbers being where they shouldn't be, when we're interpreting things as integers that are not integers. So this should not be completely surprising. Same thing happens with floats, right? Different reason though this time. Interpreted as a pointer, you get this bad boy. Can anybody tell me what representation this is? That is hexadecimal. Have you guys heard of hexadecimal? Yes? No? Maybe? Okay. So, no, that's not a question. Okay. So, we're going to be talking about hexadecimal in not too much more time, I believe. But in general, here's the quick version, right? Decimal is a base 10 number system. Therefore, digits range through 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the digits that are valid under decimal arithmetic. Hexadecimal is base 16 arithmetic. So in addition to the regular decimal digits, you also have A, which is equal to 10, B, which is equal to 11, C, 12, D, 13, E, 14, and F, 15. So you range from 0 to 15 because it's a base 16 number, right? So that's why this thing has F's and C's and A's in it, but no letter higher than F, right?
Doesn't it have an X?
Oh, yeah, sorry. These, the 0x at the front here just says this is a hexadecimal number. X means hexadecimal. You can actually have 0O to represent octal. You can have 0B to represent binary. So that's like a format designation rather than a part of the number. I'm glad you caught that. Thank you. My shoe is untied. Unrelated to manhole covers. So, you may notice that this thing is quite long. That's because it denotes an actual memory address as given in my computer system, right? So if you were to take the RAM, feed it this number, right, it would pop out the first the first number in the array. That's how it would work, right? Another thing to note, we haven't initialized this array, so the numbers that it contains before we initialize it are essentially random, but again, arrays are filled with garbage data before you initialize them, right? Make sense? before we get much further, I just want to explain the reason we use hexadecimal, right? So, decimal numbers are tricky because if you look at the underlying bit representations here, everything up to and including 7 can be represented using 3 bits, right? You have 0, 0, 0, 0, 0, 1, etc., all the way up to 1, 1, 1. Past that point, you require 4 bits to represent 8 or 9, right? 1000 and 1001, right? So, essentially, decimal arithmetic does not line up perfectly with the underlying bit values, right? Another way of saying this is the number of decimal digits which are required to represent binary information is variable. You get a variable number of digits, right? If you consider hexadecimal, 15 in binary is 1111. So, 1 hexadecimal digit represents exactly 4 bits. So, the size of a hexadecimal number is directly, the bit width is not, like the value of the number does not vary the number of digits displayed according to binary arithmetic. Does that kind of make sense? 2 hexadecimal digits always represent 1 byte. 2 decimal digits do not necessarily represent 1 byte. Make sense? Or, 2 or 3, 2 to the power of 8 is 256. So the largest 8-bit unsigned number is 255. So what if you're trying, what if your number is, 483, you need more bits, so it's not stable, right? So that's the reason that hexadecimal is used. It's always a stable representation of the underlying bits. You can always read what the binary is doing using hexadecimal characters. Make sense? Hopefully. Maybe a little bit. A little bit of sense would be good. All right. So, just like a lot of things in C, there are no free lunches. You can't print a whole array just by passing the array's name to printf, as the array identifier is really a memory address, or a pointer. So it doesn't recognize, C doesn't recognize the difference between a pointer and an integer. If you ask it to view it as an integer, it will do so. If you ask to view it as a pointer, it will do so. It doesn't care. It will just do as you ask without thinking about it too hard. An uninitialized array is full of garbage data, smelly garbage. To initialize an array, provide a comma-separated series of type-correct literals or expressions delimited with curly braces. If the initializer is smaller than the declared memory, C will backfill with zeros. If you initialize the array, you may omit the size specification, as the size of the initializing array will be used. So, do I have that before or after? Okay. So, an example of that. This bar array of floating point numbers is being initialized with 4 floating point numbers. It is not necessary to specify the size here, as that information is derived from the number of elements in the initializing array. Make sense? Good. If you have provided a number here, and that number is larger than the number of items that have been provided, then it will actually overwrite the garbage data with zeros. Make sense? Good. So, let's see. There's one other thing that I want to, I think I have slides on it coming up, so I will only talk about it briefly, but there's no such thing as an out-of-bounds error in C. If you ask for elements that are outside of the array that has been declared, C will just give them to you. You can even assign to places outside of the array. A wave of terror should have passed through your bones and made you shudder when I said that. That's right, folks. Memory is just memory in C. It doesn't actually keep track of the size of its own arrays. There's no such thing in C. So, for example, if I were to write a simple little C program, that worked. There we go. There we go. It's one of those days. Edit arrays.c. So include stdio.h. This is a live coding session, by the way, so if you want to follow along on your laptop, that would be wonderful. Int main. Sure. Unlock. There we go. So let's imagine I declare a simple array of integers. Int array. There we go. Let's make that of size 20. And let's, 0 or 1, 2, 3, 4, 5. There we go. I'm going to see if I can copy paste this. May or may not. It's including the line numbers. Terrible. Well, that's a thing. I don't know why it would do one and not the other. It doesn't make any goddamn sense. These are the wrong quotes, too. LaTeX does occasionally do me dirty like this. There. So, take that up. GCC out arrays, LC, error. Oh, yeah. Okay, I'll just change this. All right, I give in we go. So, as you can see, A, because the number of initializing values I've provided is less than the size of the array, the rest have been filled with zeros. Now let's have some fun. Let's imagine, just for the sake of argument, that I didn't manage to line these two up. I forgot, I changed this and I didn't change that, or something like that, right? Let's just say I asked for 25. I wonder what this program is going to do. So, you'll notice, first of all, because I didn't change this thing, like where it selects this one and does the closing brace, it's just doing the closing brace in the new line each time, so it's like stuck on the last case, right? But you'll notice these numbers, right? This is the memory existing past the end of the array. So, if this is my memory, this is the array as declared. Those last ones are me reading elements past the end of the array. I'm reading into uninitialized memory. Right? And you might say, isn't that kind of dangerous? Can you assign to this? Well, let's see. Let's just, for the sake of argument, C at I is equal to I. And we'll forget about this bit. We smashed the stack. So you'll notice I not only have the ability to read past the end of the array, I have the ability to write past the end of the array. And in situations where you do write past the end of the array, that is detected in certain systems as a stack smashing attack. Basically, a lot of old viruses used to use this technique to read from and write to memory that didn't belong to them. A lot of the memory protection mechanisms that are embedded in good operating systems like Linux are countermeasures to the fact that, way back, you could basically read any portion of your memory from a C program. So, modern operating systems protect you to a degree against this type of thing. But you'll notice it let me get as far as I wanted to outside of the array before it cut me off. So you might be saying, okay, so where is this memory that I'm reading and writing to relative to system architecture? This is stack memory. That's why it's a stack smashing attack, right? You can do the same thing with heap memory, which is outside of the stack. Dynamic arrays are vulnerable to the same type of thing. You might say, well, aren't there other interesting and useful things stored in your function call stack, like local variables? And the answer is yes. Absolutely. One of the interesting and useful things that are stored inside of your stack frame are local variables. Your follow-up question might be, doesn't this mean that you can use this property of arrays to overwrite your local variables from arrays without reference to the variable itself? And the answer is, why yes, that is possible. So what's the moral of this story? Don't program in C? The moral of the story, of course, is you are responsible for making sure that your arrays aren't doing this, because C isn't checking for you. Other languages will check this sort of thing for you. In fact, one of the design parameters of many languages is that they check this for you because C doesn't. But in C, this is the type of thing you have to worry about. Make sense? Question?
Is this also in C++?
Is this also in C++? Okay, so in C++ too. But, you know.
No, I was asking a question.
Oh, that's a question?
Yeah.
So, my understanding of C++ is the way they get around these types of problems is by encouraging the user to use fancier data structures that keep track of things. So, to my knowledge, and if anybody in the room is a C++ person, you can feel free to chime in on this. My understanding is that C++'s sort of default data structure they like to use is called a vector, and that it has some protections against these types of things built in. But vectors are a class rather than being sort of the native array data structure. In C++, of course, C++ is a superset of C, so you can still do this, right? Every C program is a valid every C program is a valid C++ program, even the bad ones, right? But if you use a class that protects itself against, overage in this manner, then you don't have to worry about it. So that's my understanding of how C++ handles this sort of thing. Whether or not it's accurate, yes?
Just a question. What did you change in the second time to make it not stop at 20?
I just changed the stop condition of the loop.
Oh, okay.
Here, I'll, right here, I just changed that from a 20 to a 25. So that means that, if you mistakenly put a less than equals here instead of a less than, then you are reading 1 over the end of the array. Whereas in something like Python, you get an index error, right? It's not an error. It's not even a warning that you're doing this.
So the program you said aborted, it stopped itself, right? So
Yes.
the program terminated, but it only did that after you reached the end of your for, right?
Yes.
So what if you put I as less than a million or something? Would it just
Let's try it.
Oh yeah.
I'm gonna wipe this bit though, just because I want to just read. But let's pick something large. That's large, right? Well, I probably don't need that many zeros. So you can see we can read quite a bit actually. Quite a bit. Fair amount. Quite a bit more than I was expecting, to be honest. But that's a lot of memory. But in the end, we get this little guy. Seg fault. So, segmentation fault, right? By the way, I have no idea what this data is. No idea. So segmentation fault. Very, very important concept. The operating system gives you a little sandbox, right? It portions you off a region of memory. That's your memory. Don't go outside it, right? If you request to read a memory that doesn't belong to you, the operating system will kill your process, right? It will result in a segmentation fault. So, if you want a more technical term for it, it's a segment access violation fault. But yeah, so basically, we pick some point, like, you can think of these variables as being assigned to a random place inside inside your stack frame, right? Like in terms of physical memory, it's essentially random, right? In this case, I think we ended up getting a spot that was pretty close to the beginning, right? Because we got all that data. So this loop just keeps asking for data and asking for data and asking for data and asking for data, eating up all of that existing memory until finally it asks for something that it has no permission, it doesn't have the rights to ask for. And at that point, the operating system crashes the program. Make sense?
One follow-up question.
Absolutely.
The function space, like your segments that you're allowed to touch, is that like to make sure that you don't, like, for example, like overwrite like other files on your computer?
It wouldn't be files because files are stored on your ROM, right? That's in your file system. This is RAM we're talking about. It's completely off of like the file system. You don't have to worry about overwriting files. What you do have to worry about is interfering with the program memory of other programs, right? So, like, for example, the operating system itself, right? Because everything's using the RAM, right? Everything's using RAM as its active memory. All loaded programs are loaded into the RAM, so they're all stored in there somewhere. So if it weren't for segmentation faults, and say we were overwriting here, right? It wouldn't allow us to because we'd hit a stack smashing fault first, right? But if you ended up with a seg fault, right? If there was no such thing as a seg fault, you could, in theory, jump into the program memory of another program and modify variables in like your solitaire program or your network connection software or your keyboard driver that's loaded, like, to say that you could do a lot of damage that way is to say practically nothing, right? And like, you don't know when that memory is being written back into ROM. So like, overwriting elements of your driver's memory, you don't know if those settings are being saved and at what point those things are being saved, so you could like brick your machine. Basically. Does that make sense? Okay. Y'all appreciate you guys will come to hate seg faults because you are going to have seg faults, right? You'll be like, oh, I got a seg fault. Oh, I got another seg fault. But appreciate them, for they are all that stands between you and the yawning void of chaos itself. All right? Good. I'm certain that I have a slide on seg faults coming up. But, So, and now for something completely different. So I'd like to talk about macros, just briefly. One problem that led to that whole explanation and problem we had with the stack smashing attack was we had confused ourselves and were iterating over a different number than we declared the array with, right? One way to make that consistent, well, there are a couple of ways to make that consistent. One would be to assign a variable, right, and use the variable as the size. Another way would be to create a define statement. Somewhat similarly to a type definition or an enumeration, define statements are things that the compiler takes and replaces things with before we hit compilation, right? So the the best way to think of a define statement is as a global find and replace over all of your C source code files. Anywhere the character's size are found inside of your program, they will be substituted for the characters following the space. This includes keywords, this includes like curly braces. This, the define statement is direct character substitution, right? Size is never a variable kept in system memory. Anywhere size is in the program as it's being, as it's hitting the precompiler, right? The preprocessor. Size is being, like these characters are replaced for those characters. So 256 is being inserted in the program before compilation. Make sense? Understand the distinction between this and a variable? Good. A macro is a processor command which defines a character substitution. Yes, yes, yes. We may use macros to replace all occurrences of the size string with the size we wish our array to be, thus enhancing modularity. So we can have the size of the array declared up front in a define statement at the top of the program, and then just use size everywhere that the array is, and Bob's your uncle. It only gets, if it gets modified, it gets modified in only one place, and that is that's the golden zone of software modularity that we're all shooting for. When you want to modify a program, you should only need to modify it in one place, right? Because if you're a person who didn't write the program, you may not know all of the places that it needs to be updated, right? Therefore, you will not update it everywhere. Therefore, you may run into exactly the kind of faults and errors that we just demonstrated, right? Because programs tend to be more complicated than one for loop. Any questions? Good. Macros can be used for all kinds of things, which we will be discussing later on in the course. But yes. So let's talk about arrays and how they interface with functions, which of course will be extremely relevant material anytime you try to actually use them on an assignment. Consider the following function prototype. Integer pointer, my function, constant integer input array. Input is declared as an array by the inclusion of the square braces. We put square braces here, that means it's an array. Using integer star, also valid, though it means a slightly different thing. You can also specify a size here if you want to. Int star tells us this function returns an integer pointer. Arrays in C are syntactic sugar for pointers, with a couple of extra rules thrown in regarding like read-write rules, but it's not overly important. The constant term locks the pointer so that it can't be modified. This essentially makes it read-only. So by declaring this constant, we are essentially saying that this input, the pointer to the data itself, is read-only, which can be very useful, right? This prevents any of the array's elements from being modified as well as the value of the pointer. So when you're making an array constant, it doesn't just mean that the pointer to the data structure is constant. The elements are constant too, whereas if you make a pointer constant, it just holds the pointer because it is just a pointer. Make sense? This is how arrays have slightly different read-write rules than pointers do. You with me so far? Good. If you want to be able to modify the array, just leave out the constant keyword. You can do this with any argument, not just arrays. In Python, we have the length function to quickly and easily tell us how large our data structures are. in C, we have the size of function, but as with most things in C, it's a bit more complicated. Size of returns the size in bytes that the provided argument was declared with. And it can only see things that were declared in the same block it exists in. So once you pass an array into a function, you can no longer use size of to determine the size of the array. It is very common to pass the size of the array in as a function argument to be able to tell that data. Make sense? Size of may be used on variables of any type, not just arrays, and you can also use size of on types themselves. So size of int will give you 4, size of double will give you 8, that sort of thing. Good. Accordingly, the declared length of the array is equal to the size of the array in bytes divided by the size of any element of the array in bytes. So if you want to know how many elements are in an array, you do the size of the array divided by the size of any element of the array. The first element of the array is more or less guaranteed to exist, so the correct thing to do is to use, foo at 0. Make sense? Question?
Does that mean like no matter how big a number I can put in an array, like it's still the same size in bytes as say 1 or 0?
Yes.
Really?
Yeah, the size of an integer does not affect the amount of bits that it's stored in.
Bits are stored in?
Yeah.
What was that whole tangent earlier then about how like it's in like some integers are in like 3 bits or 2 bits?
Oh, that's just how it's displayed.
Oh, okay.
Yeah, like decimal display doesn't. Decimal display has a variable number of digits that it will display versus hexadecimal, which will be fixed.
Okay.
Right? But that doesn't affect the underlying bit representation. In both cases, you hold like the actual bit values constant between those two different. You can view a number as either a hexadecimal or as a decimal or as a binary number or as an octal number. You can view binary data as an integer or as an unsigned integer or as a float, It all depends on how it's being used. Does that make sense?
Yes.
All right. But just to reinforce it, maybe not to put too fine a point on it, right? This is how things are declared, right? So you have memory, right? You have the operating system, and you have my program, right? My program might ask for an array of integers of size 20, right? So, int c size 20. Declare that, please, right? The program, given that it's C, says, okay, I want 20. These are integers. The size of the integer is 4, so 4 times 20 is equal to 80. It sends that number to the operating system and says, I would like to request a segment of memory of size 80 bytes, please. The operating system the operating system checks, well, it doesn't check memory directly. What it does is it keeps a list of what memory has been allocated to what program, right? So it's like, okay, I'm going to consult my list, see if I have space for that memory, right? Can I give that to you, right? It might return a result that says, yes, I have space to give you that memory, right? It then sends your program back a pointer to the memory that it gave, that's allocated to it, right? The program then uses that pointer and just accesses that memory, right? So we have this tendency to sort of split the thing up and think of it as a sequence of integers, right? It's just bits. The only reason it's a series of integers is because when you're accessing the elements of the array, right, that's actually what it is a pointer arithmetic with offsets. If I ask for C at 6, right, what it's actually doing is it's saying, okay, C is located at this address, right, plus 6 times the size of the data type of the array, which is in this case 4. So our new data address, the pointer at which C6 is located is, well, this is in hexadecimal math, and hexadecimal is hard, but it's, 88 plus 24, right? So it calculates the offset. It then looks up that new offset memory cell. And then it, interacts with that specific memory, that region of memory. But one thing that in the architecture course that these poor comp scis have had to deal with is like taking an array of integers and casting it as an array of single bytes. So just because this has been declared as integers doesn't mean that you have to keep it as integers. If you interpret this data as containing other data types, the data will remain constant in that array. You're just interpreting it differently. So for example, short integers, right? Short integers are half the size of regular integers. So if I were to take this guy, right? Take C, cast it as a short integer pointer, right? It does that. The same data, right? Yeah. And at that point, you start having to ask yourself questions like, is this a big endian or a small endian system? Right? Because it matters at this point whether the big end of the data is stored this way or that way. Right? Because you're dividing the integer down the middle, right? So is this the top half and this the bottom half, or is this the top half and that's the bottom half? Right? These are the types of questions that you have to answer. You have to ask yourself if you start dividing data up like this. So in general, people don't, unless they're like doing architectural stuff way down deep. That you can squeeze, like, these are the types of optimizations that C, like, you can use this kind of stuff for optimizations in C, right? But, like, this is kind of arcane C knowledge. This is like, but I hope that reinforces how, like, C thinks about memory. Does that make sense?
Absolutely.
Awesome. Any other questions? Are you, okay, before you go, are you scared of C yet?
Yes.
Good. Then my job is done.